All right, good afternoon. So what class is it that you were coming from? You guys were saying?
Yeah, 30 with Dr. Goodens.
Oh, okay. Okay. So I can blame him then. And he was torturing you with Excel, was it? Oh, perfect. Perfect. Is that the fun kind of torture, or do you actually hate it?
No. So when it's happening, kind of torture.
Wait, what was it that you were working on?
QPCR curve.
Okay. And what about the Excel part did you not like?
It was just fast.
Just fast? Okay.
Because we had to add the add-ins while he was doing it. So
Yeah.
Okay.
And there's a big long formula at the very end that
He just put it down and was like, oh, okay.
And there's also just a lot of like hotkeys that you can use that like if you don't know them,
Right.
it's like slows you
It
down.
slows you down, yep.
It stacks up, with every hotkey that you don't know.
Right.
Yeah.
So he's moving too fast, basically. Yeah. Okay.
Not as bad as Chrissy, lots of listeners. He went so fast. It was awful.
Oh. Model.
Are these also horror stories about Excel back here? Well, same thing. How do you guys feel on a more practical note about my pace in class? Is it okay? Is this helpful? Would you like to follow along instead of just have me do stuff, or? So I maybe have a day where I tell you to bring your laptops, and then I just intentionally go a little bit slower, and we build something together, kind of thing. Okay, we can do that. We can certainly do that. Okay, thank you. Okay, so speaking of that type of thing, I didn't get a lot of time to work on this because I've been in a bit of a scramble today, but I did put in a little bit of work to figure out what's going on with the MATLAB solver. And so I'll just share with you, and you can follow along if you'd like, the little bit of progress that I made working towards figuring out, okay, what was it that we need to use? And to be honest, there's probably multiple ways of doing this in MATLAB. There almost always is. But last time we were trying to use this little solve function and kind of got a little bit stuck, and then the instructions that we were finding online didn't seem to help. So I just wanted to show you, and I did this on my desktop computer, so I think I need to do it on my laptop, so this will be perfect. So I was looking into a particular function. So it was, now I'm forgetting the actual function I was looking, but it wanted me to define some symbols, so SYMS for symbols. And so I was like, oh, okay, well, what does that mean? And it said, oh, you need this symbolic math toolbox in order to use that. And so I was like, all right, I guess maybe this is like the solver add-in, or maybe it's something I have to buy. I don't know. But it looks hyperlinked, so let's click it. And then it brought me to, let me bring this over. It popped up a add-on explorer, said symbolic math toolbox. Okay. And it gave me the says create a symbolic scalar variable, blah, blah, blah. And that was something I could use with the solving equation. So I said, all right, well, let's give it a try. See what happens. So I went to install it, seemed to work fine, and then I was able to start playing with it. And I was even able to, actually I do have the file, I think. I was able to put in just a bit of code to see what happens, and it's spitting out something, but I haven't figured out exactly what it's spitting out yet. So I'll show you that in a second. So nothing conclusive, but I'm just kind of giving you a little preview of what maybe you ought to do to get this functionality into your MATLAB. A lot like doing Excel solver, right? So hopefully that is only a few seconds. Then we can get back to that. Okay. Yes. Okay, so it's going to reboot MATLAB, and then I'll show you the little thing there. And
Do you have a Mac or a PC
PC.
Okay.
Yeah.
It runs pretty slow on my Mac.
MATLAB does?
The red or the web.
Okay. So the web version may have the symbolic math toolkit already in and running. That may very well be the case. So if you're using the web version, maybe none of this matters. Would be my guess. So, all right. Of course, there's always got to wait a moment. Okay. All right, and it moved my. Okay, so I think I don't need any of that, and we'll just go back to where we were. Here we go. All right, so I think it was this. Okay, so I started just a little bit of coding this morning, and the function is called VPA solve. And that's what I was taking a look at as a tool which needed this symbolic toolkit. And basically what it says is this can solve a system of equations, and maybe I don't need a system, although it certainly can do that. Maybe I just need something that solves one equation. And then it gave me some of the syntax that looked a lot like what we were doing last time. And so I went to go ahead and try it, and I put in our equation. I put in our variable, our constants, Ka for that example we had worked, Kw, and the total acid concentration that we had in that system. And then I defined a symbol H for H+. And so then I solved, and I was trying to say, all right, well, give me the H concentration, solve for that, for this equation when it's equal to 0, and the variable is H, and then convert that to a pH. So I think I probably did something wrong, or I didn't understand exactly how it's working, because it's spitting out kind of an array. And I need to figure out what exactly is going on. And actually that looks like pi, so we're getting pi of some sort, I think. So I'm not sure exactly. I think I've done something a little wrong, but you can see just another little step of approaching this. I'll try to give you a little better guidance of, maybe there's a different solver, a more straightforward way to go about it. Yeah.
Do you use the sims command because H is just sort of arbitrary? It just kind of depends on.
That's what it looked like this function wanted, this VPA solve. It looked like it wanted some sort of an arbitrary x, solve for x kind of thing. And you set up an equation with x in it, and you tell it x is the variable that you want to change in order to make this equation true. Right. That's what I think we're doing. But even that, I could be wrong, and that could be why I'm not getting the answer I think we should get. I also have not yet tried multiplying this whole thing by 1 million. So we could even try that right now. Like last time I said, the error propagation would go a lot better if we said all of this times 10 to the 6, and try that again, and maybe we'll get that pH value. Doesn't look like it changed anything, so I'm just going to leave it there for now. Come back to you when I have a little better solution there. But I wanted to just tell you, kind of give you a little more exposure, tell you when I spent 20 minutes on it today, that's kind of the process that I've gone through. And you might need to do this solver, or the symbolic math edition. And by the way, if you master this, it might make all of your future algebra problems really simple. If you can just oh yeah, I forgot the quadratic, but I know I can do it in MATLAB. Tell it to do it, right? So could give you some pretty cool tools for other math class or other math problems. Okay, so we are gearing towards graphical solutions to our pH equilibrium problems. There's a couple more simplifications and things I wanted to introduce first. So we're going to get there with the graphs and take a while to really dive into how do we set up a graph and how can we interpret it or use it to make shortcuts for ourselves. We're going to get there. but just a couple other pieces that we will be able to see in the graphs in a few minutes. The first being another way to express the proton balance kind of stuff is sometimes used a tot H. So total H, it's kind of a comparison of the amount of excess protons we've added. It's a bit intuitive, and so you'll see this in some chemistry contexts. I'm not too worried about it. Our book just has this little subsection on it, and I've seen it around occasionally, and it's really just achieving the same thing as a proton balance equation, but just starting it from a slightly different approach. So just so you know, there's some materials out there where you can say, okay, here's the protocol, the 5 steps to get tot H. But effectively what we're looking at is how much H plus are we adding given the stuff that we added. Okay, so not worrying too much about that. If we decide we want to dive deeper, we'll do that. And maybe for titrations or something, that'll become a little more relevant. And we'll come back to it if we need to. Okay, so last time we did the solver stuff. And we were thinking about it. All right, we've got this equation. We set it to 0. And now we can use Excel or possibly MATLAB or something to solve it. And basically using a numerical approach to achieve a solution. So we're guessing, we're getting closer to our guess, and we're guessing again, and so on. And that actually might be my confusion with the MATLAB. I might be actually trying to find a analytical solution when I meant to be telling it to give me a numerical. That might be the issue. So when I was very quickly searching, okay, MATLAB solver, maybe I forgot to tell it, tell Google that I wanted a numerical solver. How does MATLAB do that numerically? Because that's the approach we were taking. And so setting up with these variables, the symbolic variables, that's actually probably more like an analytical approach, meaning we use x, like x squared plus whatever equals 0. And then we solve specifically for x. And we can do that. And here's this slide. We're going to just show ourselves why we're not going to do that, but how we could do that, right? So if we wanted to really go analytical about it, we can say, we can use a polynomial in H+. And you probably noticed this when we were working on the solutions last time. I even told you, like, all right, now simplify this in terms of H+, right? We could do a bunch of algebra and it would get gross, right? And then we'd have some sort of quadratic or cubic equation, blah, blah, blah. So here's just a little quick demonstration of what that looks like. And as this book this is not our primary book, a different book was saying, we do this only for instruction because, while it's possible, there's really no payoff, and there's a few problems. It requires a lot more work. We could make some algebra mistakes, and it's just harder to solve. So we're not really going to do this, but you can see how we could, or how the math makes sense, right? So that's all I wanted to show. So we take that left-hand side minus the right-hand side, and we can rearrange it. If you recall, we had like H plus something something over H plus Ka times At minus 1 over H plus, or something like that, right? There was H plus in all sorts of places. So if we multiplied everything by H plus, it could get it out of the denominator to an extent. And so we go from a equation that looked something like that to this equation. And we'll simplify down to this cubic equation where we have H plus to the third, H plus to the second, and H plus to the 1. Okay, so from there we could get a solution to a cubic function and find the root, right? Like doing the quadratic for a square function. But this is just not great. And if we look at the graph that this function spits out, we can see that it's not great for a few reasons, right? We might be able to use it. It might still get us that 4.57 value that we found last time. But the rate at which this is changing as we step up in pH is extremely fast. So we go from just a tiny bit away from the correct pH value is an enormously high number. And then if we blow by it just a little bit, it drops a huge amount. And then it comes back up towards 0 again. And so none of that is very helpful for for solving it. Now, maybe if we're graphing it, that's okay, but numerically, it's just not good. And then we also have this whole region over here where we're back close to 0 again. And so if our first guess was pH 10, well, where are we going from there? Is it close? It looks very close, but that's not anywhere near the real solution, right? So there's a few problems with this shape, is what I'm trying to say. And it's just not so fun. All right, but we could do it, right? It's theoretically possible. So we're going to avoid that and not take that polynomial approach. Okay, so I'm going to take a step back away from that and say, all right, let's briefly review the stuff that we know. And I meant to keep some of these pieces not showing just yet. As you'll see, I'm going to add in parts of the solution as we go. I meant to do that for the whole thing, but oh well. So take a moment, and we already have the answer, so don't worry about calculating the exact final answer, but I want you to take a couple moments to test yourself to see, okay, can I set up this problem? Can I take the first steps of writing the mass balance and electroneutrality equation that we're going to need to solve this from the materials we've done in the last few times, the last couple lectures. So the problem says we've got hypochlorous acid, this is bleach. It's a common disinfectant. We're adding 5 milliliters of a 10 gram per liter solution of HOCl is diluted to a total volume of 1 liter of distilled water. And we want to know what is the resulting pH. Not worrying about activity corrections, we're just going for it. So we have a Ka and of course the Kw we know. So take a moment and set up the problem, okay, in terms of the mass balance equation and the electroneutrality. Yeah, you don't need to, you're welcome to, but you don't need to calculate the mass balance in terms of the concentration, but set up the equations for a minute, okay? Yeah, and pretend you didn't see that for now. Oops, sorry. So hopefully one of the first things you did was just write out all the species you know about in the solution. So we've got water, of course, H plus and OH minus, HOCl, and of course OCl minus because it's HOCl is acting like an acid, or it is an acid, and that H plus can leave, right? How do you feel about it so far? You feel like you know what to do, or at least know how to start it? Okay, good. All right, so for the mass balance, the book's saying, okay, well, we have some total amount of OCl, and that's going to be the whatever, the combination of the two forms, HOCl and OCl minus. But we don't know it until we do some calculation. Right, so what is it? Well, we can do that calculation to take that 5 milliliters that we had, multiply it by the concentration we had, convert that to, because that was the concentration in grams per mole, or grams per liter, so to convert that to moles per liter, we have to do the molecular weight, and that's the part I'm saying don't worry about. We'll skip that for now, or we'll let the book do it, and we get some value of HOCl total added at 9.5 times 10 to the minus 4. Okay, then we've got the charge balance. And we really don't have any other sources of mass balance here, right? We could write out the mass action, the equilibrium values to say that, Ka is H plus times OCl minus divided by HOCl. That would be another good thing to write down so you have it on hand. One of our equilibrium equations, and of course you could do the same with Kw. Hopefully by now that's kind of second nature. This should be H plus times OH minus. Would be divided by water, but we're treating water as 1 because it's a liquid. Okay, so with that, we can get this electroneutrality equation where we balance the charges, and it should be pretty straightforward. H plus is our only positively charged species, and we've got OH minus and OCl minus as our negatives, anions. Okay. From there, we can do some derivations to arrive at our combined equation. And here's this next step of the process where I hope you can follow along or recall, make sure you're comfortable getting here. We've done this before with the HA case, and this is no different. This is just HOCl instead of HA. We've swapped OCl for A. So we've got this equation, right? I just wrote that again and right here, and it was just rearranged. We've got the OCl total, and we could start from that electroneutrality equation and start substituting pieces in as if this is A minus is equal to alpha 1 times A total. So we can do the same thing here and substitute pieces in and ultimately derive an equation that we can set to 0, left-hand side minus the right-hand side. And it should end up getting us to a function like this. Now in this case, they've done the algebra a little bit different, but it's kind of the same process, right? So I think they've multiplied H plus by both sides to get that quadratic. So they simplified it in a different manner. Maybe they started with started at a different point and simplified from there, but it's the same deal, right? Okay, so using the quadratic equation to solve for H plus, we would get 4.9 times 10 to the minus 6. And one of the things that we can notice here is if we solve for let's see, we had the total OCl is 9.5 times 10 to the minus fourth, but if we check the OCl minus concentration, we will find that the OCl minus concentration ends up equaling the H plus concentration. And there's an interesting reason for that. It's because we have made the solution a little bit acidic. Okay, so let me just read what this says. So using the quadratic equation, so solving it with Excel or whatever, in this case they put it into a quadratic and solved it that way. The concentration of OCl minus and is 4.9 times 10 to the minus 6, and pH is 5.31, and if you take 4.9 times 10 to the minus 6, sorry, I already did, blah. that is pH if you convert it to a pH, right? 5.31, okay. But that corresponds to OH minus of 2.04 times 10 to the minus 9. Okay, this H plus is also equal to the concentration of OCl minus. So why does that happen? Well, this kind of comes back to our equation down here. So if we take a look at our electroneutrality equation, if OH minus is approximately 0, then we see H plus is approximately equal to OCl minus. So this is an interesting simplification we can use sometimes when OH minus is a lot smaller than H plus. And we have a specific term for that we're going to talk about for a couple of minutes here. But the wider point is we can get a system, set up some algebra, go for solving the root of that algebra, whether it's we put it into quadratic or whether we leave it in that kind of the ratios that we had it last time and tell Excel to do it. Either way we go, we should be able to solve for a value of the pH by taking the root, right? But in both cases, it's left-hand side minus right-hand side, and you figure it out. You set it to 0 and go from there. Okay, so this simplification that I just mentioned is called the acidic solution approximation. I don't think our primary book touches on it much. So I'm not going to go too deep on it, but I wanted to let you know that sometimes we could make good use of this, and it makes things a lot easier for us. And we will see how this shows up in the graphs. So when we look at a graph, we'll notice, oh yeah, the OH minus is almost nothing here. There's also a basic solution, which is just the reverse. So, oh yeah, for very basic, the H plus isn't really doing anything. It's almost all in the other form. So sometimes we can take this approximation and say, great, this is fantastic. We'll simplify. And maybe we don't need that quadratic or the cubic or whatever. So I'm going to read a bit of text here for you. So a very logical first assumption to make for a solution of some acid HA is, well, if that's all that's in there, it should be at least a little bit acidic, right? We just added an acid. So going back to the starting point of the electroneutrality equation, if it is somewhat acidic, then there's a good chance that this becomes not very important. Now, if it's pH like 6.8, that's not very acidic. It's a tiny bit acidic, right? So in that case, yeah, doesn't hold, doesn't do anything for us, doesn't really matter. But at some point, enough acidity and suddenly the OH minus really doesn't matter in some of our calculations. So when does that happen? How does it help? Let's take a look. So if it's even mildly acidic, OH minus becomes much less than H plus. And according to the electroneutrality equation, that essentially gives us H plus is equal to A minus. Okay, so that becomes a very nice relationship that we can then use. Okay, and of course this is rather specific conditions that we can use this. Okay, so by this assumption, K water divided by H plus, that's the OH minus, we can kind of get rid of. So in our more elaborate setup, when we substitute in right? This is alpha 1 times A total. That's this part, right? So alpha 1. I'm going to clean that up a little bit. So alpha 1 times A total, this is the equation we were looking at last time. H plus minus alpha 1 times A total. Set that equal to 0. And we can do that because we were taking this here and this here. And this would normally go here like last time, but we set it to 0. Okay? So when we got rid of that term, we were left with this equation, which is just a nice simplification. So we get a simpler term, and it's right here. So now we get a second order equation quadratic, and we could use the quadratic equation if we wanted to. Or solver, because who wants to do that, right? But regardless, you see how that gave us a simpler form of our function, and now we have kind of a better starting point. So this acidic solution approximation can be very handy. And if we have any information about the mass balance on A minus, that might also be come into play and be helpful. So this is the acidic solution approximation. When can we use it? Well, if we really want to go geek optional here, the definition, or a good way to go for it, is as long as we are not making more than 10% of an error. And so the way it's defining that is to say, well, if OH minus is at least, or excuse me, at most 10% of H plus. So if we take OH minus and say it's at smaller than or equal to 0.1 of H plus, then we're okay. That's kind of a pretty good definition. And the pH scale is working on log scale, so really that means we are 1 pH away. There's 1 pH separating our two things here. And if you think about it, if you're at pH 6.5, that means your pOH is at 7.5. And so that's why we would say as long as our acidity is greater than 10 to the minus 6.5, or our pH is less than 6.5, because it's at 6.5 where we've reached 1 pH separate. 7.5 minus 6.5 is 1. So all that to say, that's when we start using our acidic solution approximation, and we're good to go. Feel free to come back and read the more details there later, but it's kind of saying approximately that. Okay, there's one other thing we can add to this, and that is whether or not we have a weak or a strong acid. So if we have the weak acid approximation, a weak acid, something like HOCl, does not fully dissociate. So we will have some HOCl and some OCl minus. And what you'll notice is once we put that in water and the water is acidic and we're well below the pKa, it will almost all be in the HOCl form. And that can help us simplify, because now we know from a mass balance perspective, as long as we are far enough into acidity below the pKa, then our mass balance gets simplified. So it's another way we can simplify our setup. So this is meaning HOCl is not dissociating, and the alpha 0 becomes close to 1, approximately 1. So that means we can set up a mass balance saying our A total under these conditions is approximately all HA, or in my example, HOCl. So at pH 5, when chlorine dissociates around pH 7.5, at pH 5, it's going to be like 99.998% or something like that, HOCl. So that's what this assumption is saying. We can treat it pretty much as a new mass balance, saying it's all in that form. This is the opposite of the case for a strong acid, right? A strong acid just dissociates and is dissociated throughout the whole pH scale, essentially. Once you get, I guess, below pH 1 or whatever the definition was, maybe not so much. But for normal cases, the strong acid is the inverse. It's almost all going to be the, if we used HCl as the example, it's all going to be the Cl minus, the A minus version of it. So we can define and talk about all these things. And just real quickly, I'm just going to show how this can apply. So we can say if Ka, that's our acid dissociation constant, is a lot smaller than H+, that means we are much more acidic. It's a lot more pH. Excuse me, there's a lot more H+, it's a lot more acid. We could also say the pKa is a larger number than the pH. Kind of inverts it that way. For a weak acid in acidic conditions, then we can simplify because this guy, when we compare these two numbers, the Ka becomes kind of irrelevant, right? It's almost as if this is 0. And a good way to think about this is if this was 1, let's say 10,000, and Ka was 1, 10,000 is a lot bigger than 1. And so it's kind of like that 1 doesn't matter. If you take it away and don't calculate it, it's really just one distant decimal place change, and it's not going to affect our calculations, right? So that means this equation becomes something quite simple. So I'm just going to say this is becoming approximately 0, and that's only in the denominator, right? We still have it in the numerator, and it has no other reference point. So even if it's a small number, it's still an important number because it's not getting swamped by that big number H+, right? So if it was 1 over 10,000 plus 1, the 1 is important on top, but the 1 is not important on the bottom, right? Okay, so this then becomes, if we were to write it out, H plus minus Ka over H plus equals, times At equals 0. And if we multiply everything by H plus, that gets rid of the H plus, it becomes H plus squared minus Ka times At equals 0. And then from here, we get this equation, right? So that's pretty convenient. We could simplify things that way and get a very simple solution for what is H+. Well, as long as we know the total amount of acid we've added and we know the Ka, here's the pH value. Does that make sense? So we could go back then and solve some of our equations. Instead of using the solver, we could take a look as long as we know the total acid and the Ka, and as long as these two conditions are met. There it is. It's pretty simple. Okay. All right. If we do a strong acid approximation, strong acid, a good example is HCl. And I'm just going to write a very faint backwards reaction because it's not really happening under any normal pH. Would dissociate to H plus and Cl minus, right? Theoretically, we might be able to contrive a condition with a negative pH that doesn't really exist, where it would find equilibrium in the reverse. But in reality, it doesn't happen, so it's a strong acid. That means the amount of acid is approximately equal to A minus. If we look at our electroneutrality equation, which should have been H plus equals OH minus plus Cl minus, the OH minus, like we said for the acidic solution approximation, that's from the acidic solution approximation. So now H plus is approximately just Cl minus. And in fact, whenever you've done pH calculations in simple scenarios, I think I even gave you some of these in your first homework, just to assume nothing else, and this is the only source of adding protons, this is what we did, right? We said it completely dissociates, and that just pushes a bunch of acidity in there. And so this is just the elaboration of why that makes sense. So whenever you solve a solution like that, this is kind of the why. So A minus is basically all of the concentration there, and that also means H plus is going to be equal to that total concentration. This is that strong acid approximation with also the acidic solution approximation. Okay, does that make sense? Okay, for the sake of the class, I don't want to get too far into this. We'll probably do a little more practice on this and include some of this, those two pieces. But I think I will probably, unless the titration stuff makes it convenient or meaningful to use the base stuff, I'm not going to go too far into the basic solution stuff. It's exactly the inverse. Okay, so you already, if you learned the acidic part, you now have learned the basic solution approximation, right? So we can look at acids and bases exactly in the exact same manner. We just have to invert the way we're thinking and treat OH minus as if it's H plus. Okay, so we could do the exact same things. We just haven't been talking from the basic perspective very often. When we get to titration, we'll do that a little more. But I just wanted to say it's the same deal. Just from the base perspective, we can have a strong base, a weak base. We can have a basic solution approximation defined in the same way, right? pH 7.5 and above. Or we could even say pOH at 6.5 or below to really mess with our minds, to look at it that way. But just wanted to say all of that's going to hold true. It's the same system as acidic, just for basic. And we can do the same with the weak base and the strong base. All of that would come out to be the same exact calculations, just for solving OH minus instead of H plus. Okay, so want to go from there into finally graphing these systems and looking at a graph to be able to determine what's going on with our pH system and perhaps being able to arrive at some conclusion or some answer based on looking at a graph that we've made. Okay, so there's a few ways we will often graph problems like this. One would be a log-log plot, where we have, let's say, log of some concentration here, maybe log C versus log pH. Sometimes we might just take a fraction. We've done alpha before, so alpha versus pH. Of course, we can also do just a concentration versus pH. We've seen those also. But I really want to focus on the log-log plots here. And sometimes you'll also see, instead of log C, you might see PC. And in the case when we get to some of the redox chemistry, we'll look at PE, which is an electrochemistry or like a redox potential value that we might be interested in. So we'll see plots like that. And one thing you can note is for any aquatic solution, we know that the concentration of OH minus and H plus are defined. And they're defined exactly because Kw equals H plus times OH minus. And that value equals 10 to the minus 14. So that means right here is defined, right here is defined, and here and here. All of those are defined by Kw. Okay? And even when we say, all right, what happens when H plus is equal to OH minus, that's the same thing as saying Kw is equal to H plus squared. And you solve for H plus and you get 10 to the minus 7, which defines exactly here. Right? So all of that information, these lines, are defined right there. So anytime we draw any kind of a log-log graph, or log versus pH graph, we know we could draw these two lines. So no matter what else happens, those are going to be there. We don't necessarily always need to put them there, but we know they're there, right? So that's kind of the first simple step. Next up, if we have a monoprotic acid, so the simple HA case, it's going to look a lot like this, where we have on the left side, this will be in the HA form. And we know also, by the way, that this is some form of a weak acid because we have existing HA in the system at some, somewhat normal pHs. And we have A minus on the right side because the more basic we get, the more the protons leave to form water with an OH minus. Just taking the protons away as much as we can. Where the reverse happens, if we're acidic, there's tons of protons around, so it protonates the A minus into HA. Okay, so we know that. We've talked about that a lot. We also know that wherever these cross, this is going to be the value of Ka. We also know that at that point, so that's true. And we also know that that's the point where alpha 0 equals alpha 1, which is equal to 0.5 or 1/2. We could also say that up here around this spot, alpha 0 is just about 1, and up here, alpha 1 is just about 1. Right? That's the ratio of what is A minus versus the ratio of what is HA. So all of that we've learned before. I'm just starting to write it out and make it nice and clear. And I've got a couple slides that are going to do exactly this and even better writing than my handwriting, my beautiful handwriting. Okay, so an interesting thing to consider is, well, what's happening in between in these zones where we're not really equal, right? We're not really close enough to 1 to call it 1, right? That's going to be an interesting spot to look at. Okay, so kind of on the theme of the alpha fractions, we can actually take log of the alpha fractions and perhaps find something pretty interesting. Okay, and another interesting way to simplify our systems, and I think this is actually probably a log alpha plot now that I'm thinking about it. This is, so and sometimes we will have log alpha. Okay, so in these log alpha versus pH, again, we're going to use a monoprotic acid, just HA. By the way, we can do all of this stuff with diprotic and triprotic stuff. We're just keeping it simple to figure out the basics at the moment. We have HA in equilibrium with A minus and H plus. Maybe this is ammonia. Maybe this is, HOCl, whatever the case, and I guess in the case of ammonia, that's slightly different. We've got the plus and the neutral, but whatever. Doesn't matter too much. This dynamic is going to happen, right? Alpha 0 is, we can describe as the amount of HA per total. Alpha 1 is the A minus per total. And if we take the log of both of these, if we just take the log of both sides here, say log of this and log of the other side, what happens? Well, the log rules tell us when we have a division, of x divided by y, and we take log of x over y, that becomes log of x minus log of y. I mean, we could leave it all in one thing, but we can also separate it and simplify. So that's what we've done, and I'm just going to improve my writing here a little bit. Of course, we just take the log of both sides, just shorthanding it that way. So now we see we can solve for the log of HA is equal to log of this alpha 0 plus log of A total. And of course, if we wanted to, we could have left it and said this is log of alpha 0 equals log of HA minus log of AT. Right, that's also fine to write it that way. And we can do the same thing for the alpha 1 equation. Okay, now I'm saying this because when we pause a moment and think about this, log of alpha, if we can get one of these other pieces in terms of pH instead of these variables, then we can suddenly plot on a log-log plot, we can plot a linear relationship very conveniently. Okay, so that's kind of where we're heading. So we're going to assume activity is 1, and if you remember our alpha values, we can also define them and derive these expressions, pulling in the equilibrium equation and putting it in terms of Ka and H plus. So we can get this piece in terms of Ka and H plus. All right? So we're going to come back and kind of see this a little bit in action. And I'm going to take a look at the graph now. So we'll probably call back to that in a couple minutes. So here's another graph. It's very much what I was sketching out, but it's all written there nicely. Even tells us this pKa plus or minus 1. That's kind of the transition zone where the interesting things are happening and where we can't really make these assumptions that alpha 0 is 1 or alpha 1 is 1, right? The other thing we can notice is the slope of these lines, the log alpha lines, is either 1 or minus 1. And that is going to make sense when we pause and think about what I was just saying. If we plot log of alpha equal to some function, if we can get that function in terms of log H plus, there's a good chance, at least in the monoprotic system, that's going to be a slope of plus or minus 1. And that is actually how it works. Okay, so in this particular scenario, our pKa is 5, and so 5 is where they cross. And we can get a lot of information there. We know HA is equal to A minus there. And the log of alpha 1, we can say is equal to log K divided by K plus. Whereas log of alpha 0 is log of H plus divided by K. So here's where we have the slope. It's 1 times that log of H plus divided by some factor, or 1 times log of Ka divided by H plus. Okay, so I'm going to take a step back for a moment and read through this with you. So when we take a look at the system, there's a few things to note. And so this should hopefully clarify everything that I've just talked about in a nice, simple, direct form for you. And just pardon me a moment. I'm getting slightly distracted by the conversation. Okay, so the curves for log alpha 0 and log alpha 1, I think is what they meant to write. They're going to cross at pH is equal to pKa. That's, when we know we've hit the center point, and we know alpha 1 is equal to alpha 0, that's 1/2. The other thing we can note is the distance, and I'm going to zoom in here a little bit. So when we find that crossing point, it looks something like this. The distance from here to here is always going to be the same. So that distance is going to be equal to negative 0.301. And that comes out from the log calculation. So if you take, let's say, some total concentration there and divide it by 2, so 1/2 if 1 is the total, and take the log of that, the log of 1/2 is 0.3. that's where we're getting the number, okay? Or maybe it's negative 0.3. Well, you know, the math will work that way. No matter what the case is, when we've reached that halfway point, that's how much of a drop we have on our graph. So we can always hold that to be true. Maybe we plot this and we say we have a total concentration. So a total might be 10 to the minus 3. And then we would say, we could use this to say, well, at 1/2, that should be 10 to the minus 3 minus 10 to the 0.3. You know, we would minus the 0.301 from the exponent there, and we could find our new concentration. And that would always be the case. We don't have to do it that way, I'm just pointing out that would get us there. Okay, so that's what this second point is making. Okay, so then point 3 says each of the log alpha lines has two nearly straight asymptotic legs. That's out on the left and out on the right, where, you know, the slope is approximately 0 and log of a is equal to log of approximately 1, which would be 0, right? So up here, that's basically just saying alpha 0 is approximately 1, which means the log of alpha 0 is 0, and alpha 1 is approximately 1 over here. So log of 1, of course, equals 0, right? So on this graph, we might be drawing it from 0 to minus 1, minus 2, and so on, right? If this is a log alpha plot. Okay, last step says for log of alpha 0 line, the second leg has a slope of minus 1. So this is, we'll say m equals minus 1 for the slope. And of course, on the reverse, that's plus 1. Okay, and then we know that they're going to cross in some sort of transition zone. At that point where pKa is equal to pH. All right. Okay, so there's a couple things we can do using these acid-base simplifications to apply it to the graphs. So it's kind of tying the two pieces in. We talked about this acidic solution approximation, basic solution, all that. Now, how does that apply to the graphs, or how can we kind of see this show up? Well, if we have pH a lot higher than pKa, that's a very basic solution compared to the equilibrium point, right? So we are much further to the right on a graph, or sorry, to your right, right? So we're much further on the right for a graph of the pH graph. That means we're in a much more basic condition. That means H plus is a lot smaller than Ka, right? Or pH is a lot larger than pKa, and by a lot larger, we're saying that it's at least 1 log difference. Okay, so as long as those conditions are met, then we have a situation where the alpha 0 can be simplified to approximately H plus divided by Ka. So we'll recall that alpha 0 is normally this guy, right? Normally we say this is H plus divided by H plus plus Ka, but under these conditions, this guy is approximately 0, which means we have H plus over Ka. So from there, we get this. And likewise, when we take a look at our alpha 1, we say, well, if alpha 1 is defined as Ka divided by H plus plus Ka, here again, the H plus goes to approximately 0. And we could say that this is Ka over Ka, which is 1. Now, that seems very simple, right? It just equals 1. Well, let's take a look at our graph. When does alpha 1 equal approximately 1? When it's very basic compared to the pKa. So immediately it's like, oh, duh. If this is the pKa, and we're saying that the pH is off here much further to the right, much larger than pKa, then yeah, alpha 1 is 1, right? Approximately. So that's kind of where the graph and the algebra intersect, right? We can see exactly why that simplification ends up working, because this one comes over to here. So now let's take a look. What does alpha 0 look like? Well, that's going to be h plus, which is a very small number, divided by Ka. So as we move to the right on the pH graph, we're getting a very small number as the numerator, and smaller and smaller and smaller. And now if we take the log of that, the log of alpha 0 equals the log of h plus minus the log of Ka. Log of Ka is some constant, and so it's a -1 slope as we travel along pH. So we can say log of alpha 0 in this section is going to be equal to log of h plus, which is like saying negative pH, right? Minus log, I'm going to move this out of the webcam, minus log of Ka. So log of Ka is a constant, so this would be the same thing as saying negative pH plus pKa. Okay, so that's, or pKa minus pH. So that's describing that line. That's why it's a first order, or rather a slope of 1 going down. Okay, does that make a little more sense now, connecting these dots? Sorta? Okay, and on the other side of things, we could do the same calculation. This is a very basic condition. We could do the same calculation under a very acidic condition, and we'll see the same result come out for the alpha 1 case under acidic conditions. Okay, so essentially what I've just written, or what we had earlier, is written up here. So I'm going to give you a little example to work on. So it says, this example is for quickly estimating alpha values based on pH and pKa. So let's see if you can kind of apply what we just talked about to a couple little problems, and there's no calculators needed. You might just have to add or subtract some number. Okay? So part A says, and I've got 2 graphs here for us to use for A and B, just kind of sitting here, and a little space to write. We'll say, all right, so part A says a solution containing ammonia has pH of 8.10. Without any calculations, give estimates of alpha 0 and alpha 1. And we know that pKa is 9.24 for the ammonium ion. So think about what we were just talking about and consider whether or not pH is a lot greater than pKa, or if the reverse is true, it's a lot smaller than pKa. What can you simplify about the alpha equations, right? So alpha 0, that should be, I think this was H plus, I'll double check this in a second, over H plus Ka from right here. And alpha 1 was very similar, but Ka divided by H plus Ka. So part A asks about ammonia, and the pKa is 9.24, and the pH is 8.10. And the second one is asking about some acetic acid, where we have a pH of 6.6 and a pKa of 4.76. So you should only have to add or subtract and just think about how these things simplify and get the answer, okay? And feel free to work together. I see a lot of you feel like you're not quite sure where to start. You can ask me for help too.
I guess I'm a bit lost.
Okay. About where to start, or? Okay. So can you guys, let's take the first one, right? So solution A. I'm going to label the pKa, right? And I'll label the pKa on both, right? So pKa equals 9.24. And we know the pKa is here, right? So if we label the x-axis here as pH, then this right here is 9.24. Okay? And then I guess somewhere up here is 14. This is probably not 0 because we're not drawing the full scale, but you can imagine it would extend to 0 eventually, right? Okay, so with that, then find pH 8.1, right? Maybe if each one of these things is about 1, maybe we'll give ourselves a little more space and say that's half or something. No, this should be probably 1. These are probably 1 also, right? So let's move it a little more than 1 to the left. Would be something like right here, right? So this should be pH 8.1.
So the log alpha naught ticks are on the left, and then the log alpha 1 ticks are on the right?
That is a very, very good point. We probably should label these, right? So this will be pH on the x-axis and log alphas on the y-axis. That will probably help quite a lot. Okay, so starting by just simply drawing things will hopefully help. And do that for both of these. See how it goes.
you think we wouldn't be able to use the negative pH plus pKa is equal to the log of alpha naught? I guess because I got a value of 1.14,
Uh-huh.
which would be outside the bounds of
A value for what? For the pH or for what do you calculate?
for the log alpha naught.
Okay, so log alpha naught, you got a value of 1 point what?
1.14.
Okay, so if you take a log of 1.14, what do you get?
0.05.
Okay, does that sound reasonable? Like if you take a look here, do you think, so remember we can also label here, this should be alpha 0 and this should be alpha 1, right, for every of these graphs. Does that look like it's a correct answer for this case?
Well, I guess it should be getting more negative as it's.
Are you solving for alpha 1 or alpha 0, first of all?
Alpha is 0.
Okay. Yeah, so eventually at higher pHs it should be getting more negative, or more, it should be getting smaller, right? The alpha fraction, but the log alpha should be getting larger because it's, or a larger negative number, right? Okay, how many of you feel like you're just completely stuck? Anybody? Okay, how many feel like you've got partway there? Kinda? Anybody like feeling just totally lost? Kinda? Okay, so we're just gonna take a look at this and look at the solutions together. And actually I realized I probably wrote over where the solutions are gonna show up. But a couple things to note here, I'm just gonna rewrite the pH, is it's going to be good to draw everything that we can and then think about whether or not we have these simplification things. So for part A, we can take a look, and we said if the pH is a lot smaller than pKa, that means one thing. And by a lot, we meant 1 log difference, right? At least 1 log difference. So for A, pH is at least 1 log difference below pKa, right? So we can simplify something. And if we take a look at our graph here, and where we are interested in is right here, to see what is the value of the alpha 0 and what is the value of alpha 1. And if nothing else, we can say this is 0, minus 1, minus 2, and so on. We can just make a guess that alpha 0 is a small fraction, or excuse me, is the log of alpha 0 is close to 0. And the log of alpha 1 is probably something like minus 1 to 2 range. That's the bare minimum we could do just by sketching stuff out here, not really drawn to scale. Okay, so but that could guide us to say, okay, well, what approximately are we looking at? Now, in order to like solve some algebra, we could say, let's take this solution and say, we just learned there's some way to simplify this. So if pH is a lot smaller, and let's start with the alpha 0, let's say alpha 0 is then approximately, if H plus is not really going to matter, let's see, if that's going to be the reverse. So we had talked about alpha 1, so I'm going to start with alpha 1. Like the last slide was alpha 1 related, right? That was, I guess we talked about both. Let's start with alpha 1 for a moment, because that's when on the right-hand side of this, we have a simplification because this guy will become approximately 0. So on the right-hand side, alpha 1 would become approximately 1. I'm sorry, that's not at all relevant because that's not where our pH is, right? Our pH is less than. So it's the Ka that goes to approximately 0, right? So in this case, Ka is much smaller than H plus, and so we can write alpha 1 is equal to Ka over H plus, and we can take the log of all of that to find some algebraic way to describe that, to say log of alpha 1 is going to be log of Ka minus log of H. And if we put all those pieces in, that will say pKa, well, negative pKa minus negative pH, so plus pH. So let's take a look at the solutions. It says, and I'm going to get rid of my writing here a little bit. Okay, so for A, we have 9.24 minus 8.1 is that 1.14 number that you actually mentioned here. That's pKa minus pH. Okay, so where did that come from? That's coming from doing some sort of simplification. Under these conditions, the Ka became a lot less important than the H plus on the denominator here. Of course, we can do the same thing and look at the Ka becoming a lot more important for this one, and it's going to change the equation. So I'm going to erase a little bit of stuff. You know what? I think what I'll do is I'll start back here and give ourselves a little more space to write it out more clearly next time. So just real quick, these numbers are coming from that simplification, and we don't really need a lot of math because the log forms give us it in those forms, and that's kind of the trick. Now, I don't think I was very clear, and I would like a little more space to make it clear, so we'll start here next time.